Uh, so it helps, the biosphere and life near the surface. Much of the ozone is produced in the tropics, and it's transported poleward most strongly in the winter hemisphere by the Brewer-Dobson circulation. So if you look during December, January, February in the northern hemisphere, you see these darker blue colors building up of the thicker layers of ozone. You see the same thing in June, July, and August in the southern hemisphere. But another thing that happens when you get into September and October is you see a thinning over these whiter colors that show up over Antarctica. And I'll talk a little bit more about the chemistry and some of the unique stuff that's happening over Antarctica. Next slide, please. Another instrument on the AURA satellite is the microwave Lim Sounder. Okay. So the MLS measures total column, it measures profiles of ozone as well as a number of gases that are important for ozone chemistry. I'll talk about some of the temperature measurements, water vapor, nitric acid, as well as hydrochloric acid and chlorine monoxide. So during the polar, in the winter over Antarctica, you see very cold temperatures, and this causes condensation of water vapor and nitric acid to form polar stratospheric clouds. So whether it's ice or nitric acid trihydrate, these are surfaces on which chemical reactions can take place to turn a reservoir species like hydrochloric acid into an active species like chlorine monoxide that causes ozone depletion. And so here you see the ozone concentrations very low in the polar vortex in winter. But this just basically shows some of the measurements that can be made with the AURA's microwave Lim Sounder. Next slide, please. A nice resource that we have at NASA is the Ozone Hole Watch website. And so you can track the ozone hole season and see how things compare to other times. This is an example from 2017, from this past season. You can see the ozone hole area and the minimum and how it changes over time. There's an equivalent in the northern hemisphere during March, during winter in the northern hemisphere into spring. But it's really interesting. You can see the ozone hole minimum, how high it was sort of in the 1970s, and gradually getting lower and lower during the 1990s. And now in the early 2000s, the mid 2010s, we're starting to see just the hints of recovery beginning to show themselves in the Antarctic ozone hole. But it's a very slow process for this recovery, and we expect it over the course of the 21st century. Next slide, please. This just shows a monthly composite of ozone minimums. This is just for each particular year when the minimum occurred. From 1979 through 2016. So you see the high values, you see some particularly dynamically active years, particularly low ones when after Pinatubo went off. You'll see a high year 2002 right there. I'll talk a little bit about 2002 as a pretty interesting dynamically active southern hemisphere. And you can see this start to come back up towards the end of this record. But it's a very slow kind of recovery, and it's just starting to emerge in some of the data sets that we look at. Next slide, please. One of the things that I do at NASA Goddard Space Fund is run chemistry climate models. And so one of these new products that we're working on is MERIT-2 GMI. This takes the MERIT-2 dynamics, so the winds and temperature and pressure, and constrains that with an interactive chemistry for the stratosphere and troposphere. So this shows hourly images of ozone as it's evolving over the 2002 season. And you can see on the right is the observed time series. And we have times where there was instrument outages. You see in between swaths during the polar night where we don't have observations because it's measuring backscattered ultraviolet radiation. So this just shows we can get a composite over the course of a day with some missing areas. But models help us to understand what's going on and fill in those gaps. And right here in September, you start to see an elongation of the polar vortex. And for the first time on record that we had these observations, the vortex in the southern hemisphere split. So it's a very dynamically active, and you'll see the two lobes, and it matches very well with the observed record. But you can see that this winter was pretty unusual. It was a very dynamically active winter. And so this just shows ozone moving around the vortex with the low values in the center, and the white colors represent the higher values. So this product, this model simulation, is at 50 kilometer, half a degree resolution, and we have it from 1980 all the way through 2016. So it'll be very useful because we can look at not only ozone, but all the different gases that deal with ozone chemistry. It can be looked at, it's a global, so it can be looked at throughout the world, in the northern hemisphere, in the tropics, but just showing an example of what we can do over Antarctica. Next slide, please. So chemistry climate models, not only do they help us understand past changes in ozone, but also projecting the future evolution of the ozone layer. And so the red curve, this goes from 1960 to 2100, is a simulation. This shows the October minimum ozone. The red dots are a model simulation, and the white is the observations. And you can see it matches up quite well over the past. And this kind of gives us an idea of what we can expect. So 1980 levels of ozone, we sort of expect that in around 2060, 2070 time frame. So it's these chlorofluorocarbons that we emitted into the atmosphere a lot of them have very long lifetimes, 50 to 100 years. So even though due to the Montreal Protocol and subsequent amendments, they were phased out, they remained in the atmosphere for a long time. And so you see this recovery, but it's over much of the 21st century. So it's slow, and we are observing this, and we can model this impact. And so we use these observations to tell, how well are we modeling this? Do we understand all the processes? Is there things that are missing from our models? Next slide. Another project I was involved in is looking at the world avoided. So in around the 1970s, chlorofluorocarbons were growing at about 7% per year. We took a conservative estimate of 3% per year and continued it out into the future. What if action was not taken? What would have happened to the ozone layer? So this is the world that we expect that's happening. You can see the seasonal ozone hole that's forming in the southern hemisphere, but you see generally higher values throughout the high latitudes. If you look at the world avoided, by the 2020s, you see the ozone hole is no longer seasonal. It's year-round, the dark blues. And then you start to see in the northern hemisphere an ozone hole forming. And this is the level of chlorine. So instead of, say, 3 ppb, this is a factor of 10 higher. But you also see that these values, when you look at the blue colors, these are getting sort of below these ozone hole 220 Dobson unit values globally. So this was a really, very fortunate that we had the science to help us understand this, that actions were taken, and that we're not headed on this path of the world avoided, because the effects for the biosphere and life are quite harsh. So this is some of the things we can do with models to understand how well do our predictions, how well do they pan out, and what are some of the things that were avoided by the actions that were taken. Next slide, please. So I just want to come back around to what I showed in the beginning. This is the OMI record of total column ozone. And this is just a thin layer that we have in the atmosphere, but critically important for protecting us from some of the harshest ultraviolet radiation, which is linked to cancers, and also high ultraviolet radiation damages plants. So the effect on crops and things like that. It really is one of the most critical observations that we have, and one of the critical constituents in the atmosphere. And this ozone record is one of our longest records. Now we have satellite measurements going back to the early 1970s, but continuous sort of from 1979 on. So it represents a really important climate record that we have, and we hope to continue this in the future. I'd be happy to take any questions. Thank you for listening.